So, good day everyone. I'm Amalor-J and as for my topic for today is about infiltration and percolation, process and measurements. And for infiltration, it is the process of entering rainwater into soil strata of earth. Infiltration term first used by Hortons to describe the phenomena of soaking water into the soil. And it is also defined as the downward movement of water through the soil surface into the soil profile. Infiltration is the means by which groundwater supplies are recharged and water is made available to sustain vegetation. And as for percolation, comes from the Latin word percolare, which means to strain through. Percolation happens when liquid is strained through a filter, like when someone makes coffee. Then it is also the process of downward movement of water into soil once water enters into the soil. It is also the movement of water within the soil matrix. So, infiltration and percolation are often used interchangeably. However, percolation specifically refers to the movement of water within the soil, while the infiltration refers to the water entering the soil surface. So, and when percolation stops, infiltration also stops. But when infiltration stops, percolation continue. Next is methods in determining infiltration. So, there are 5 methods, which is the infiltrometers, observation in pits and ponds, placing a catch basin below a laboratory sample, artificial rain simulators, and last is the hydrograph analysis. First is the infiltrometers, which is there are 2 types. First is the double ring infiltrometer. It is a simple instrument which is used to determine the infiltration rate of water into the soil. It consists of open-ended inner and outer rings that are driven concentrically into the soil at a given depth. Outer ring water fills soil voids in the lateral dimension, leaving inner ring to vertical flow. The inner ring must be significantly smaller than the outer ring. The diameter of the rings are typically 20 cm for the inner ring and 30 cm for the outer rings. And the penetration depth of the metallic rings is usually limited to 5 cm to minimize soil disturbance. Also, the double ring infiltrometers minimize the error arising from lateral flow of water compared to the single ring method. So this is the double ring infiltrometer and I have a video for example for double ring infiltrometer method. So, next is tube infiltrometer. This consists of a single tube about 22.5 cm diameter and 45 to 60 cm long, which is driven into the ground at least to a depth up which the water percolates during the experiment, and thus no lateral spreading of water can occur. And the water added into the tube at regular time intervals to maintain a constant depth is noted, from which the infiltration curve can be drawn. So this is the tube infiltrometers. Next is observation in pits and ponds. By noting the depression in the level of water in the pits and ponds and deducting the loss due to evaporation, an idea about the infiltration rates in such soils can be obtained. Next is placing a catch basin below a laboratory sample. By placing a catch basin called a lysimeter under a laboratory sample or at some depth below the land surface, the infiltrating water can be measured and the infiltration rate in the soil can be obtained. Next is the artificial rain simulators. On a small area of land of 0.1 to 50 square meter, water is applied by artificial showers at a uniform rate. The resulting surface runoff is measured and the infiltration capacity of the soil is determined. So this is the example for the artificial rain simulators. So next is the hydrograph analysis. By knowing accurately the varying intensities of rainfall during a storm and the continuous record of the resulting runoff, the infiltration capacity can be determined and discussed in the next chapter. So next is the infiltration rate. The infiltration rate is the velocity or speed at which water enters into the soil. And it is directly influenced by soil texture, soil cover, moisture content of the soil, soil temperature, precipitation type, and rainfall intensity. Infiltration rate at which soil is able to absorb rainfall or irrigation. It is measured in millimeter per hour or inches per hour. Then if I, which is the rate of rainfall, is greater than F, which is the infiltration capacity, runoff occurs. So using Horton's equation, F is equals to Fc plus Fo minus Fc raised to E raised to negative KT, which is for K is equals to Fo minus Fc over Fc, where F is the infiltration capacity, Fo is the initial rate of infiltration capacity, Fc is the final constant rate of infiltration at saturation, E is for the base of the Neperian logarithm, and K is constant depending primarily upon soil and vegetation. T is for time, and Fc is the shaded area in the figure. So this is the figure and that is the shaded part. So and if I is greater than or equal F, then Fa is equals to F. So in this situation, it's depend upon soil capacity, where I is the rate of rainfall, F is the infiltration capacity, and Fa is the actual infiltration capacity. And for this situation, which is I is less than F, then Fa is equals to I, which is this equation depend upon this situation depend upon rainfall intensity. So next is the infiltration indices. Infiltration capacity of soil does not remain constant. In hydrological computation, for computing surface runoff and flood discharge, the use of infiltration capacity curve is not convenient. It is more convenient to use average constant value of infiltration. So as for infiltration indices, for consistency in hydrological calculations, a constant value of infiltration rate for the entire storm duration is adopted. So for infiltration indices, there are three types, which is first is the phi index. It is the average rate of rainfall above which the rainfall volume is equal to surface runoff volume. So based on this hyetograph, to determine the phi index, which is the horizontal line is drawn on the hyetograph such the shaded area above that line is equal to the volume of surface runoff, while the unshaded area is actually represents all the losses including interception, depression storage, and infiltration, but is assumed that all these losses are due to infiltration losses only. So this is the formula for phi index, which is P minus R over T, where P is the total rainfall, which is in centimeter, then R is the runoff and also in centimeter, and TA is the time period for rainfall excess, which is in R, and the phi index is in centimeter per R. So next is the W index. So it's the average rate of infiltration during the period when the rainfall intensity exceeds the infiltration rate. So this is the formula for W index, which is W equals to P minus R minus S over T, where P is the total rainfall, which is in centimeter, the R is runoff, which is also in centimeter, and T is the total time period if I is less than to FP, and S is the total losses, which is also in centimeter, and C is the runoff coefficient. So this C is andito siya, which is C is equals to I minus W over I, and R, para makuha ang R sa taas kay ganito, kay kon siya, R equals to CP, which is yung C is the runoff coefficient. So the next is F average index, or the infiltration capacity average index. Then in this method, an average infiltration loss is assumed throughout the storm for the period I is greater than F. So for like yung pag yung sa runoff ba yun siya? Throughout the storm for the period if the runoff occurs. So this is the example for infiltration index. The rates of rainfall for the successive 30-minute period of a 3-hour storm are 1.6, 3.6, 5.0, 2.8, 2.2, and 1.0 centimeter per hour. The corresponding surface runoff is estimated to be 3.6. Establish the phi index, also determine the W index. So by construct the hyetograph as shown in this figure. So makuha na natin yung I, which is the rainfall rate of rainfall, which is the 3.6, 5.0, the 2.8, and the 2.2. So by following this formula, nakuha na natin ang phi index, which is 1.6 cm per hour. And for the W index, which is 1.5 cm per hour. And next is supra-rain technique. The rainfall in excess of a particular value of phi index for the entire pattern of storm rainfall is called suprarain. Then allowance for areal variation of rainfall and F capacity is made by dividing into sub-areas in the case of large areas. So this is the formula for the using suprarain technique, which is P net mean is equals to total of area times P net dash 1 over area, which is the P net mean is the mean hourly net rains. Then the P net 1 dash 1 and P net dash 2 is the net rains in the sub areas. Well, the area 1 is the total area of the catchment in the area 1 and area 2 is the sub areas. So this is the example for suprarain technique. Hourly rainfalls of 2.5, 6, and 3 cm occur over a 20 hectare area consisting 4 hectare of phi index is equals to 5 cm per hour and 10 hectare for phi index is equals to centimeter per hour, and the 6 hectare of phi index is equals to 1 centimeter per hour. Derive hourly values of net rain. So by following the formula, makam up na itong total net rain na 3-hour storm, which is the 4.25 centimeter. So next is the steps in determining percolation rate. So we have five steps. We have 5 steps in determining the percolation rate. First is the dig holes. Dig at least 3 holes, which is 4 inches to 12 inches depth. Second is roughen sidewalls and bottom. So roughen or scratch the sides and bottom of the hole with a knife or nails driven into a board. Remove all loose material and place about 2 inches of 1/4 to 3/4 inch clean gravel in the hole to prevent bottom scoring. And next is the pre-soak soil. Carefully fill the hole with clear water to a point at least 12 inches above the gravel, being careful to avoid washing soil into the hole. Continue to add water until the soil becomes saturated. The next is the measure soil percolation rate. Then measure the percolation rate the day after the saturation process. Record the readings on paper and store with the on-site system records. And the last is calculate percolation rate. So the percolation rate is the average time in minutes required for water to fall 1 inch. Record the percolation test data from each hole. Divide the number of minutes elapsed by the drop in inches. So I have a video here example for determining the percolation rate. So here's the video.
All you need for this test is a shovel, some water, and a ruler. Step 1 is to dig a hole, about 1 foot in diameter and 1 foot deep. I'll come back when I have that done. So I finished digging my hole, and of course I picked a spot with lots of rocks, but that's okay. Whatever you find, dig the hole there. It should be about 1 foot in diameter and about 1 foot deep. Those measurements aren't real exact. As long as you're close to that, it will work. Then what I'd like to do is get rid of all the loose soil in the bottom. You want a fairly hard bottom because that'll make measuring easier later. If you want to check your hole, get your ruler, check a depth, make sure you have at least 12 inches, and I have about 14 inches here, and that's okay. Now what we do is we fill the hole with water. We want the soil around this hole saturated with water before we start the test. So fill the hole and don't do the test until all the water has run out. Sometimes that only takes 5-6 hours. Other times it'll take overnight depending on your soil. The easiest way to do this, fill the hole, come back the next day and finish the test. For today, I left my hole sit overnight, and by morning it was completely drained. So what I've done now is refilled it with water, and then you take a ruler and just measure the depth. Stick the ruler in until you hit the bottom. You can take your finger, mark where the water line is, pull it out. I've got 9.5 inches. Write down the time and the depth, and then come back later and do it again. Now as far as the time interval goes, you can do this a couple different ways. To keep the math simple, just come back once every hour and keep doing this until the hole is almost empty. If you're good at math, you don't have to worry about doing it on exactly 1 hour intervals. Just come around whenever you feel like it, take a measurement, mark down the time, and then you'll have to calculate what the intervals are. What we want to do is get a rate of dropping of water per hour. And I'm going to show you how to do that calculation in a second.
Now that you've collected your readings, what do you do with it? This table shows the results for a typical measurement. You'll see that the time intervals have been done in 1 hour increments, and beside each one is the depth measurement. It started out at 11 inches, and after the first hour it dropped to 8.5. To figure out how much the water dropped, just subtract those two values. 11 minus 8.5 gives you 2.5. That tells you that the water dropped 2.5 inches per hour. Do the same with the other time increments, and then take all of your drops per hour and average them. That will give you your average perk rate, which in this case was 2.5 inches.
So that's all